my pleasure to be here. Today I'm going to talk about the strategies to improve 3D simulation accuracy using 1D simulation for the CFB boiler. Before talking about the main topic, I like to show what I have been doing with the barcoders. So it's some examples of 3D numerical simulations case for design verification. First one is drying and combustion of kettle menu. We designed the 5 ton per day pilot plant and simulate the bubbling flies bed combustors. Second is for the CO2 gasification system for pressurized CFBC. So yeah, it's a pressurized system. It's about 10 bar. And next one is the pilot test leak of AN catalytic reactor. So we designed the pilot reactor and test the, it's also the pressurized conditions. This slide shows the some examples for the flies bed gasification systems. It doesn't work. So first one is bubbling flies bed gasifier for waste oils. And the second one is the CFB gasifier for waste biomass. This is a gasification system of 15 ton per day, and we check the hydrodynamics with the barcoder. And this one is the dual flies bed gasifier for biomass to liquid project. It's linked to the Fischer-Tropsch synthesis process, and we check the hydrodynamics and the reactions of the steam. It's an indirect gasifier. And this is the fast pilot systems. It's a ton per day pilot scale fast pilot system. And yeah, here's the, so we can make oils from biomass. And then based on this experiment, we designed a 100 ton per day fast pilot system. And we like check the design with the barcodas, and you can see that the numbers, design value, and simulation result is really satisfactory. And next one is now we are on it's ongoing work. So we are developing a commercial scale. It's a bubbling flies biomass gasifier. So 50 ton to 70 ton per day, and here's the gasifier here. This is the bubbling flies gasifier, and yeah, this work is done by ANSYS Fluent. So we check the yeah, you can see there's some comparison with the design value. And yeah, this is the I collect the target CFB boilers we've been working on. This is research scale boilers, small scale pilot test leak, and demonstration scale is like 10 megawatt thermal and 2 megawatt electrics, and these are the commercial ones in Korea. So from small one to this is the largest one. It's a Samcheok CFBC. Was the maybe now it's the second world largest CFB boilers in the world. So we have been using 3D simulation for a long time, and today I'm going to talk about the result from this project. This project is about the developing oxy combustion system for CFB boiler, and I'm in charge of the numerical simulation part. So in the research center, we have a 0.1 megawatt thermal combustor. Its height is 10 meters, and diameter is like 50 centimeters. And you can see that, yeah, we calculate the this system. And here you can see the comparison between the experiment and the numerical simulations. Yeah, there's some difference here, you can see. And here you can see some simulation result for a demonstration plant. Its height is 14 meters, and its capacity is 2 megawatt electric. So this is the air combustion case. And so next one, this is for the oxy combustion case. So we have to tweak the reaction models for the oxy combustion case. So you can see the particle volume fractions, CO2 and the O2 inside the boiler. Okay, this is the commercial one. It's 30 megawatt electric industrial CFB boilers. You can see that it has a large cyclones, and there is a mechanical valve here, so you can separate the circulating particles. Some of the particles goes to the sectionize the external heat exchanges. Quite complex systems. And then while we conducting these simulations, we wanted to compare the simulation result with experimental result, but for the large boilers, we don't have much data. And then this is a topology of a large supercritical CFB boiler. So you can see that this is a PSE of the feed, and when it goes into the boiler, many things happens. The combustion reactions, attritions, fragmentations, elucidation, and there's a separation. And there's some loss of light particles in the cyclone, and the return of the particles. And there's a bottom edge discharge. So everything is coupled and it's very complex. So we realized that it's very hard to define the problems. So correct problem definition is quite hard. So we decided to use co-simulation, 1B3 co-simulation. And this table, I took it from the previous conference, and you can see that there's best practices, and most of them is related to the problem definitions. We don't know exactly the total amount of solid in the boiler, types and properties, compositions of particles in the boiler, and yeah, you can see that it's really hard questions to answer. So it's a good idea to use co-simulations, and we have to understand the structure of the boiler system. So here there's in the bottom there's a dense bed, and there's a splash zone and transverse zone, and there's bank mixing, and bank mixing is very important for the heat transfer. So we can simplify this system into a 1.5 dimension. So let me introduce the IFBC model. You are maybe familiar with this model, and then many experts took part in development of this model, and it's a very nice model. There are so many models in there, and then we've been working with this original model for a long time and upgraded it very much. So now this is the we named it PP version. So now it's pretty upgraded version compared to the original version. So this is one example. So we adapted two functions for the decay of the solid concentration in the axial height. So you can see that this is the original model. So with the one decay functions, there's a big discrepancy between the experiment and the simulations. But with this upgraded model, you can see that it's well away with the experiment. And there are many models in the IA FBC model. So we want to check every details of each model. So we collaborate with people in Chalmers. They collected a lot of data from their demonstration plant over 3 years. They share, and this is it's 13.5 meter boilers, and this is the operating conditions of the boiler. And then here's one example. You can see the pressure drops along the height. This solid symbol is from the Chalmers, and by changing decay model, we can fit the experimental data nicely. And this is more result here. So it's pressure distribution along the height, and then it's the effect of the superficial velocity from 1.8 meter per second for 4.7, and you can see that the 1D simulation is really well with the experiment. You can see some coefficient change for the model, and then this is the effect of the mean particle diameters from, you can see the result. Now by verification of the models, we can estimate correctly the overall hydrodynamic characteristics of the laser. So how about the local? So maybe we can check the PSD of each height. If we correctly estimate the PSD of each height, then we can say that now we can estimate the whole plant in a good way. So this is the experiment from the Chalmers, and this is the simulation result. You can see it's not good yet. So we change the some coefficient for the attritions. It affects to the size of the particles, and also it affects to the overall pressure drops along the height. And we can also change the fragmentation coefficient with the attrition coefficient. And then you can also change the model for the bottom edge discharge and for the cyclone efficiency. So you can compare the result with the experiment for the overall hydrodynamics. And this is one result. So with this coefficient, we are very this is a very satisfactory result, I think. So this is the pressure distributions and solid concentrations. And this slide shows the PSD of the left side is the sand only. They measure the PSD of sand from the boiler, and this is the whole samples, including char and ash. So you can see the large particles here. So by changing the coefficients for the various models, we can match the two result, experiment and simulation. So this is the dense bed regions. The height is like a 0.5 meters. And for different height, dense bed region, and it's 3.7 meters, 5 meters, and 8 meters. There's some discrepancies, but it's because we are trying to fit the model for the dense bed regions for this case. But we think this is acceptable. So now this result shows the co-simulation of the 1D and 3D simulation. So this is again experiment from Chalmers, and red line is the 1D simulation. And this open symbol is the Barracuda simulation with the experimental conditions, the PSD from the experiment. And then this triangle is the using 1D simulation result as the input condition for the 3D simulation. Then you can see that the result is very similar to the experimental result. This is another example for a small test leak. So again, this is an experiment, and red line is the 1D simulation, and this blue line is using 1D simulation as an input condition for the 3D simulations. When you use the experimental condition for the 3D simulations, it's very hard to fit to the experimental data. Yeah, we can do a trial error, but with this 1D simulation method called simulation, it's very easy to find the correct problem definition conditions. So temperatures and gas compositions, it's very nice. And we conduct the simulation with open form, and you can see that this case, it shows the similar result with the experiment in Barracuda. And with the 1D simulation code, we developed the GUI-based software. We named it FBR body. It's a fluidized bed reactor's body. And there's a CFB modules, BFB modules, and the DFB modules is under development, and then design body. So these are some features of the this GUI-based software. So one can use very easily this 1D simulations, and then there's also option for making an input file for the 3D simulations. So. And this is some important features of the software. So operating conditions and pre-calculation, you can get a result, and various types of reports you can generate. Some additional functions. And then this is a lighter version of the FBR body. So we can use this 1D model for this. We made this software for operators. It's very simple versions. So let's show you. So everything is already in the software, mostly for the geometry and the selection of the model. Then if you put the thermal input or the amount of air or the fuel, then you can immediately get this kind of result. So it's like online manuals or something like that. So it's very easy to understand how it works in the boilers or the reactors. Or you can change some geometry, so you can use it for check the design of the reactors. So this is the last page. So I'd like to summarize. So I show you some result about the development of 1D simulation tools, and using 1D simulation result as the input condition for the 3D simulation. So it was very effective. So we can get a very nice result compared to the experiment. And we think that this 1D simulation is very useful. You can check you can use it for the conceptual design, as I said, 1D, 3D safety cost simulation is very effective, and you can make big data and then using it for machine learning. So, if you want to have some specific profile, then ask the machine learning program what kind of PSD do I need, then it's tell you the result. And then I understand that there are many researchers from PSRI, and then I think it's very nice to use for the educations. I use it for my students, and then it's very easy to understand what's going on in the Liger and then the boilers or reactors. So you can see the result straightforwardly in a very short time. So it takes 1 minute to get the result. So I think that this is also very good tool for the education for the fluidized bed systems. Okay, this is my end of my questions, my presentation. So thank you for your attention. Yeah.